Okay. All right. So today we'll continue with polynomials. I want to focus today on integer polynomials, so polynomials with integer coefficients. The last lecture was, we didn't really talk about that. And what we'll see is, when we start talking about integer polynomials, the problem is they start to become a lot like number theory. Okay, so we'll see that today. But first, let's start with the two problems I said I would review. So these are from the homework last time. Okay, great, Karan, you were able to join us. Great. We just started, so we're starting with the review of last time's problems. Okay. So the problem says you have a polynomial which satisfies this functional equation. P of x squared minus 2 equals 2 times p of 2x squared minus 1. Okay. So any ideas we can start? Or even any observations about, this polynomial, what it could satisfy. Okay, great. Yes, so we can plug in x equals 1. Thank you for the comment, Abdullah. Right, so why x equals 1? The reason x equals 1 is because these two inputs, x and 2x squared minus 1, they become equal when x equals 1. Okay, so if you wanted to make these numbers equal, okay, one way you can do it is x equals 1. You can also, I think, also do x equals 1/2, but that's easier, right? So, okay, so what does it tell us? It tells us p of 1 squared minus 2 equals twice p of 1. Okay, that's not it's not wait, it tells us what p of 1 is, but it's not really a very nice number, right? So it tells p of 1 equals c, where c squared minus 2c minus 1 equals 0. Okay, and you can check this isn't a polynomial with any nice roots, so it's just some number, right? I don't know, 2 plus or minus square root of negative
It's
7 or
minus two,
something.
not -1.
Uh, yes,
Isn't it c
minus 2.
squared minus 2c minus
Yes,
2?
yes, 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 yes. You're right, you're right. It's minus 2. Ah, what did I, yes, it's minus 2. You're right. Yes, it's minus 2. Uh, yes. Okay, yeah. So it's just, but the point is, this number isn't very, I don't know, a nice number. Like you can solve it. So it's just some number. Okay, that's all. Yeah, okay, it's 1 plus root 3 and 1 minus root 3. Okay, so, okay. Um, okay, so what can we do from here? So there's a trick here. Yes, okay. There's another comment. Yeah, so you want to introduce a new polynomial. So, the one way to use this information we got that p of 1 equals c, this number that we know, is to say, okay, we write p of x is equal to, well, we can do polynomial division by x minus 1, and we can write it as something like q of x times x minus 1 plus c, where c is one of these two numbers. Okay. So it's just an equivalent way of writing this statement. So these two statements are equivalent, but the second way allows us to plug it back into the functional equation. And we'll get something for q now. Okay. So let's see what happens. we will have q of x squared, x minus 1 squared, plus okay, so that's true. Yeah, so what happens? It means 2 q of 2x squared minus 1, but times 2x squared minus 1 minus 1 plus c, yes? Is that right? Yeah, is this correct? You guys understand what I did here?
Yeah, I think, but we're just missing the +2 or -2 in either on the sides.
Ah, you're right. I'm missing a minus 2 somewhere, right? Where am I missing a
We
minus
can
2
just put,
here?
yeah, or we can add +2 on the other side. Doesn't really matter.
Okay, great, yeah. Like this. But, okay, no, but it's important I need that, because otherwise I would have written something wrong, because now the nice thing is because, like what is C? C satisfies this. So actually these terms here, they cancel.
I think we should have 2C in the right
Yes?
hand side.
Yes, it's 2C.
Yes.
Yes, I made a mistake. Yes, yes, so this is important. Yes, you guys are catching the mistakes I'm making. I'm very bad at doing arithmetic in my head. So yeah, so we have these. But the point is, okay, it's good because now we have the correct thing, and the correct thing tells us that these cancel, right? Because of this equation. Um, so good. So we can cancel this and this, and now what's left? So what's left? Hmm.
How do we have -4 at the right hand side?
So I think it came from. Oh, maybe we don't have -4. You're right. There is no
Yeah, we don't
-4.
have
I'm
that.
just
We only have a -2 on that side.
there's no -4. Okay, and then because there's no -4, then it cancels. Yeah. Now it's okay.
Yes.
Yeah, now it's okay. Okay, great. Thanks. Sorry for that. I was doing. I knew it would cancel, but I was doing the arithmetic wrong. Okay, so that's good. So now what? Now we can actually factor out x minus 1 everywhere, right? Because this one becomes 2x squared minus 2, which becomes x minus 1 times x plus 1, right? So we can factor. Okay. So it becomes q of x times x minus 1, q of x squared, x minus 1, plus 2c q of x equals what? Equals 4 q of 2x squared minus 1 times x plus 1, yes? Is this right? Yes. I think this is correct, yes?
Yeah, it's correct.
Okay,
Should be.
yeah. So now, what can we do from here? It's not obvious that this is any better than the equation we had before. But okay, it's similar. Yeah, so right, so thank you for the comment. What we should do is we should realize we have the same thing where the only inputs the polynomials take are x and 2x squared minus 1. So again, right, there's q of x, q of x, q of 2x squared minus 1. So if we want to get a nice equation, we can plug in x equals 1, right? All those inputs will become the same. So yeah, let's do that. So do I need more space? Maybe I need a little bit more space. Okay, so let's now plug in x equals 1 again. And what does it give us? So the first term, this will be 0. And this will be 2cq of 1. Okay, so 2cq of 1 is equal to, then what? Then we'll have 4 times 2, so 8. 8q of 1. Okay. And now, okay, what does it mean? Well, c is a number. It's okay. It's not equal to 4. So the two sides won't cancel. So in particular, it gives us that q of 1 is again equal to 0. Okay. Great. Yeah, so q of 1 equals 0. So what does it mean? Yeah, so it means x minus 1 divides q of x. Thank you for the comment. So it means when we were here, we said p of x equals q of x times x minus 1 plus c. Okay, we could have said p of x equals, say, r of x times x minus 1 squared plus c. Okay, so what it means is, yeah, we can write p of x, some other polynomial, x minus 1 squared now plus c. Yeah? Okay, so does anyone see where this is going? Yeah, so it's kind of yeah, so Abdullah, your comment is induction. So it's kind of induction. So what does it mean? Like the next thing you can try, I think it's a reasonable thing to do, just because of what we just did, is you can now, you can take this guy and you can plug it into the functional equation and you'll get something for r. And what I claim is when you work out what it means, it'll tell you r of 1 equals 0. So you can show sort of by induction that x minus 1 to the n for any n divides p of x. Okay, so what does that mean?
B of
P
x
of
equals
x
c.
is this.
So you guys spoke at the same time. I didn't.
Go ahead now.
I think yes.
We will have b of x minus c equals 0 and b of x equals c.
Exactly, right? So we're looking at, if it tells us p of x minus c is, divisible by arbitrarily high powers of x minus 1. Okay, so p of x minus c is 0. And then we'll get p of x equals c. Okay, so that's what that means. So I won't do the details here because I think it's just some kind of calculation, but you should do it on your own. But yeah, so what's the conclusion? The conclusion, I don't know, I don't have much space to write it, but I'll just write. The conclusion will be, you can show by induction x minus 1 to the n divides p of x minus c. And so it follows that p of x minus c is 0. And so the polynomial is constant. Yeah, so there's two solutions, right? There's p of x equals either 1 plus root 3 or p of x equals 1 minus root 3. And both of those work. Okay. Great. So any questions? Good. Yes, this is a nice problem. It's just, it's another application of this principle that, when we talk about polynomials, we have to go between roots and divisibility. Right? Okay. Yeah, so it's a great question. So Abdullah is asking, is there another way to solve it using x equals a half? So where did that come from? So remember, why did we pick x equals 1? It's because we wanted the two inputs to be equal. Okay, this is a very common functional equation technique that you have a functional equation with a lot of different inputs to your function, try to make them equal. Now, x equals 1 works, but there's another number that makes it work as well. You can take x equals a half, right? If you take x equals a half, it's true that x and 2x squared minus 1 are equal. So is there another solution that works like that? I didn't try it. I suspect something very similar works. Did you try it, Abdullah? Maybe you tried it and you were able to see some kind of. Okay, here. I think more or less the same thing should work, but you can try it and see what happens. I don't know. So it's a good idea, and I suspect more or less the same argument will work. But I could be wrong. Okay, I see. So maybe, okay, so you're saying maybe it doesn't work. So okay, so it's possible. I don't know. So I don't know. I didn't try it, and so maybe you're telling me it doesn't work the same way. I don't know. Okay, so let's go to the second problem. So yeah, the second problem says find all polynomials with complex coefficients that satisfy this functional equation: p of x squared plus 1 equals p of x all squared plus 1. So first, I want to make an observation that, well, okay, maybe I'll ask this question first. Can you guess some solutions? Like, it's possible without doing that much work to guess some solutions to this functional equation that aren't true, yeah, it's possible to guess some solutions. Well, okay, can you guess one solution? Let's start with that.
P of x equal x.
Yeah, so P of x equals x, that's probably the first solution we should guess, is that P of x equals x is a solution. And now, I claim it's actually, without too much work, it's possible to guess another solution. In fact, many more solutions. But you have to understand something about what the functional equation is saying.
We have some constant solution. The solution c over c squared minus c plus 1 equals 0.
So we can take px equals c.
Yeah, but it will be a complex function. So it wouldn't be like a real constant, it would be a complex constant.
That's okay. I allow the polynomial to have complex coefficients. So let's just say find final polynomials with complex coefficients. Like, for example, in the previous problem, it also had complex coefficients. No, it did not. I'm wrong. Okay, but yeah, it's okay. We can allow complex coefficients. I think it doesn't. I think it's still solvable. I think you can find all solutions where the polynomial have complex coefficients as well. Okay, so that's one. Yeah. So, okay, so here's an observation. Let's define the polynomial, let's say, maybe give it a good name, t, call it t. T of x is x squared plus 1, okay? So the observation is that the functional equation can be phrased very nicely, sorry, functional equation can be phrased very nicely as saying p of t of x equals t of p of x. So in other words, it's saying it doesn't matter in which order you apply the polynomial to an input, the same. So from here, does anybody have any idea how you can maybe guess some solutions?
B equal T.
That's right. So the solution that you can guess from here is that P of x equals T of x, because then the functional equation works, right? Because what does it give you? The functional equation is T of x equals T of x. And it works. Okay, so P of x equals, so P equals T is a solution. And now I'm going to push this one step further. Are there more solutions?
Wouldn't P is equal to negative T be a solution as well?
Let's see, P is equal to negative T. I think it works, right? Because it does work, but oh wait, that's a little, let's be clear. So negative T squared. Yeah, so let's see. I think it works, right? So if I put P of x equals negative T of x, does it work? Let's see. So it would mean negative T.
It will not work.
Or it
No,
won't
never
work.
mind. It doesn't. Yeah, it won't.
T of negative T of x, right? So T is even, so this is T of x. And yeah, it will not work, right? The two sides will be negatives of each other, right? Yeah, so it doesn't quite work. Okay, so any other ideas for something that could work?
Well, we know that P of x has to be strictly odd or even.
Why?
Because if you plug in the original equation, the x is equal to negative x, you get that P of x squared plus 1 is equal to P negative x squared plus 1. And you get that
Okay.
P of x squared is equal to P of negative x squared. Thus, it has to be either odd or even. No other function would work.
Okay, great.
So we
yeah,
can't
so
have a function that's not odd or even.
So let's plug in, let's see, x equals, let's plug in negative x, yeah, to the functional equation, right? So then we get P of, so it will still be x squared plus 1. And on this side, we'll have P of negative x squared plus 1. And so if we compare it with, yes?
Yeah, we get that P of negative x squared is equal to P of x squared. So
Right.
it has to be either odd or even.
So, okay, so this is good. So you're right, but we still need to give an argument, right? It's not obvious that just because, right? Because what is, okay, what it means is that for each x, P of x equals x, or P of x equals P of x, no, sorry, I'm saying the wrong thing. It means for each x,
The absolute value of P of negative x is equal to the absolute value of P of x.
that's right. And yeah, that's right. So they have the same absolute value, but okay, let's just write it explicitly. It means that for each x, P of negative x equals P of x, or P of negative x equals negative P of x. Okay? But it doesn't tell us that the function is odd or even, right? Because what would even mean? Even, like, odd or even would mean that, like, either this is true for all x or this is true for all x. Like it's, do you see the difference? It's the order of the quantifiers matters.
But we can use Eigenvalue principle.
No.
We have Eigenvalue principle. We have
What is that?
infinitely many Eigenvalue principle.
I don't understand the words. The what principle?
One of counting that says if we have infinitely many numbers and
Yes,
want
yes.
to we have infinitely many numbers that satisfy one of these. Each one of them satisfies one of these. We want to separate them into two groups, so at least one of them will have infinitely many.
Okay, very good, very good. Right.
For example,
So Karan, before we go there, let me first explain. So you're explaining the solution, right? So let me first actually just explain the problem. So Abdullah,
okay.
you made a comment. This is the pointwise trap, and I want to say that yes, this is the pointwise trap, right? So just because we have p of x equals p of negative x or p of x equals negative p of negative x pointwise, it doesn't mean that either is true everywhere, right? So do you see it's like it could be for some pairs of x and negative x, it's even, and for other pairs it's odd. But it doesn't mean that the function as a whole is even or odd. Does it make sense what the issue here is? Okay. Azam, does it make sense what the problem here is?
Yeah.
Okay. Good. So that's important, right? Yes,
What
Karan,
is
you have-
pointwise trap?
So pointwise trap means okay, it's like this. It's exactly this. So maybe I can just say it very explicitly, right? So okay, what I mean is this. Like, so let's say I have a problem that's like show f of x. Let's say f is some function from. Just show f of x, some function is either even or odd. Okay, so let's say I've shown that for each x, f of x equals f of negative x, or f of x equals negative f of negative x. Okay, so I've shown it pointwise. Okay, so at every we're thinking of like the real numbers, the complex numbers as a line. We're saying at every point this is true. It doesn't mean we're done. So this is just called the pointwise trap. Does it make sense, Carl?
Can you go over it again?
It's exactly this thing where sometimes you have a functional equation and you want to show that let's say you want to show something is true as a function. So you want to show that f of x is either even or odd. So what does it mean? It means you want to show it means I want to show that either f of x equals f of negative x for all x, or f of x equals negative f of negative x for all x. Okay? That's what I want to show. But that's not equivalent to showing this. Right? This is weaker. This is saying
Yes.
for each x, yes? So that's why it's called pointwise trap. This is a pointwise statement. This is a global statement. That's all. So I'm just saying it has a name, or Abdullah is pointing out that it has a name. The point is called the pointwise trap, or the name is the pointwise trap. Does it make sense?
Okay. Yes.
Yeah. Okay. Yeah. So that's all. That's all. But now you're saying there's a way to get around it, which is okay. So we've established that this is true. P of negative x equals p of x, or p of negative x equals negative p of x. But in this case, because we have polynomials, there's a way around it. And you're saying the first thing we should realize is that it's true that This is true for each x. But in fact, it means one of these statements is true for infinitely many x. Right? Okay. And therefore, we know that whenever a polynomial identity, it's true at infinitely many points, it's true as a polynomial identity. Right? Does it make sense? Maybe I can just say it a little bit explicitly. So what we're saying is, okay, maybe I can erase this. So, great, so we have this. And so what it means, from this last step, it means there either, one, there are infinitely many x such that p of negative x equals p of x, or two, there are infinitely many x such that p of negative x equals negative p of negative x. Or sorry. Negative x equals negative p of x, right? So one of the two happens infinitely often, and that means it's an identity, right? So for example, if this is infinitely, if we're in the first case where this happens infinitely many times, then it means that p of negative x minus p of x has infinitely many roots. So in fact, it's 0. Okay. Yeah, so does it make sense? So the conclusion is that either p is even or p is odd. Okay. So let's go back. So let's go back. So all of this, the point of all of this whole argument was, no. The point of this argument is to conclude that p is even or p is odd. Okay. So in particular, for polynomials, it means that either all the exponents of p are even numbers or all the exponents of p are odd numbers.
I think if b is odd, then the only solution in this case will be b of x equal x.
Yeah, great. And why is that? So yeah, so Karam has a suggestion about the odd case. So let's focus on the odd case. Maybe I can create a new. Yes, let me create a new page. Okay, great. So I want to say here what I want to rotate. Yeah. Okay. So let's focus on the case where p is odd. Let's say case 1. P is odd, and now claims that the only solution is p of x equals x. So what is the argument?
I think if b is odd, then we have the constant term of p will be 0, right?
Yes.
So we have b of 0 equal 0.
Yes.
And b of 0 from the functional equation, we have b of 0 squared plus 1 equal b of 0 squared b of 0 squared plus 1. And so we have b of 1 equal 1.
Great. So we plug in 0. Yeah, so let's plug in x equals 0. So we get plug in x equals 0, and it gives us p of 1 equals 1. Great. Okay. Excellent. P of 1 equals 1.
We have if and we go back to the functional equation. We have b of x squared plus 1 equal b of x squared plus 1. If for some a real number a, b of a equal a, then we have b of a squared plus 1 equal b of a squared. B of a is a, so b of a squared plus 1 will equal to a squared plus 1. So
if
we have
right. Okay, so you're saying if a, p of a equals a, then p of a squared plus 1 equals a squared plus 1. Right.
so we have the sequence a sub 0 equal a, and ak plus 1 equal ak squared plus 1, a sub k squared plus 1. This sequence, all of it, this infinite sequence, all of its term will be a roots of b of x minus x.
Great. Yeah. So the point is, this is a very nice observation. It's a very powerful observation because now what do we do? So we saw p of 0 equals 0, then we got p of 1 equals 1. But then, we'll get p of 2 equals 2, okay? And then we'll get p of 5 equals 5, right? And so on and so forth. And so,
So there are flexible.
That's right. So yeah, so I guess let's say it rigorously. We say a sub 0 equals 0. So yeah, so rigorously, your argument is define a sequence a sub 0 equals 0 and a sub k plus 1 equals a sub k squared plus 1. Then a0, a1, so on are all solutions to p of a equals a. Okay. And in particular, the sequence is increasing. So it's an increasing sequence of real numbers, so there's infinitely many. Yeah. So has infinitely many roots, hence p of x. Oh, sorry. I meant p of x minus x has infinitely many roots, and therefore p of x equals x. Right. Great. So any questions about this this argument? It's very nice, right? This is the key observation here, right?
But don't we only show this in the case that k is an integer, or like x is an integer? We can never actually show the, for example, p of half is equal to half.
Oh, no, but what's the point? We showed that for all these numbers, 0, 1, 2, 5, and so on, all of them are satisfying p of a equals a. Which means p of x minus x has roots, right? What roots? It has roots 0, 1, 2, 5, and so on.
Yeah.
So it has infinitely many roots. But it's a polynomial. Polynomial can only have finitely many roots unless it's 0.
Yeah, let's see.
Right. This is the trick we did last time. Remember when we were solving what? This is like last time, remember we had this problem that was like p of k equals k over k plus 1, or like k equal to 0 through n or something, and the degree has some bound, right? Okay, so we found something which is equal to 0, not for everything, but for enough values that forces the thing to be 0. So here, we don't know what the degree of p is, but it doesn't matter, right? Because we just said that this identity p of a equals a holds for infinitely many numbers. So it just must hold always. Does it make sense?
Yeah, thank you.
Yeah, so this is a very important thing about polynomials, right? What we call it polynomial identities. In order for a polynomial identity to be true, it just has to be true for infinitely many numbers. Okay. Okay, great. So right, so this is great. This we handled one case completely. This is the case where P is odd, right? So we know if P is odd, then P of X equals X. Great. Okay, so let's go back. Yeah, so what do we have? We know always P of X either even or odd. And we know if it's odd, it's P of X equals X. So now we have to think about the even case. So for example, the even case should include this solution here, right? We know P of X equals X squared plus 1 is a solution, right? And that'll be part of the even case. So here's something. If actually, okay, before actually I go there, I want to go back to the problem I asked before, which is we noticed that you can rewrite the functional equation like this. This is an equivalent formulation of the functional equation. Can you guess more solutions using that? Right, so from here we guess that P of X equals T of X works. Okay. So here's an observation. The observation is you can actually guess something else. You can say, let's take P of X equals T of X. Okay. So we iterate the polynomial. We take X squared plus 1 and we plug it into itself. Now, what happens? We do P of T of X and T of P of X, they're both the same. They're both the triple iterate. They're both T of T of X.
So the applied k times of x will always be a solution for any k.
That's right, yeah. So in general, what is the point? You can take T of, you can do this, what is called this big iteration. This will always work, okay?
So it's X squared plus 1 all to the power of k.
No, it's not like that. It's not X squared plus 1 all to the power of k plus 1. So let's it's important to understand what exactly this means. Because it's weird, right? So let's add a page after. Yeah, let's go to a new page. Okay, so what does it mean when I say T of X, many times, right? So okay, T of X is X squared plus 1. What does it mean T of X? Well, this means X squared plus 1 squared plus 1, okay? But what is T of X? This one is now
All
I
of
have
that squared plus 1.
That's right, it's all of that squared plus 1. So in particular, T of whatever, k times, so like T, let's call it T like this, okay? This has degree, what is the degree? It's squares, right? So it doubles each time. So it's degree 2 to the k, right? And, for comparison, x squared plus 1 to the k plus 1 has degree 2 times k, much smaller, right? So these solutions, they're insanely big polynomials. It's degree is 2 to the k. But they work, okay? And Actually, so let's think about it. Are these in the even case or the odd case? These are all even, right? Because you can see they're all even because they're all exactly right. They're all functions of x squared, right? They're yeah. Okay, so we see in this even case we have a lot of solutions. But okay, so let's go back. We want to understand the even case, right? We want to understand what are the even solutions to this functional equation. So any ideas?
Can we not write what we wrote on the previous page, that t of x is equal to x squared plus 1, and t k of x is the set of solutions?
Mm-hmm. Well, I didn't claim it's all the solutions. I just claimed that they are solutions. I don't know if there's more, right? I want to understand if there's more. Right. But okay, we can say this, right? Okay. So we're trying to understand the case where p is even. So let's say suppose p is even. So let's maybe let's so yeah, let's recall the functional equation. It's what is it? It's I forgot already. P of x squared plus 1 equals p of x squared plus 1. And okay, and so let's assume p is even. Okay, so in particular it means p of x equals p of negative x. Okay. But if you think about what it means, like what is p of negative x? P of x is the same, like if you think about the writing the polynomial explicitly, right? Like if I have x squared plus 3x plus 1, p of negative x just means that I reverse the sign on the odd coefficients. So on like the odd powers. So it means that p has only even powers. So in particular, because p has only even powers, you can write it as p of x is equal to, say, q of x squared for some polynomial q. Okay. So any ideas what we can do from here? So what we can do, it's like what we did in the previous problem, right? The previous problem, as soon as we understood that, like in the previous one, as soon as we understood that p of x is like this, we plugged it into the functional equation and got something for q. So we can do the same thing here. We can, where did it go? Nope. I've lost. Here, yes. So we have this, and we can sort of plug this into the functional equation. We can get something for q. But I claim before you actually do that, there's a little trick you can do. So what you do, you write q of x equals r of x minus r of x plus 1. Okay. And this is okay. R is just or equivalently, it means that r of x equals q of x minus 1. Okay. So it's a little, I just shifted the input. So I shifted the roots. It's some kind of straightforward thing. But what it means now is that p of x is equal to r of x squared plus 1. Okay. So what does it mean? If I were to somehow, like, let's say I wanted to claim that these are all the solutions. They all come from iterating T. This is a very nice thing because it's telling me that what is P? P is some polynomial R applied to T. Do you guys see? Like what this another way to write this, this is R of T of X. So what it means is if I could argue that R is also a solution to the functional equation, then I could just go down by induction. Do you see now? Okay, maybe I need to okay. Maybe I need to let's do it explicitly. So let's okay, do you guys understand the substitution I did here? Like does it make sense that this is true? Like that there exists a polynomial R so that this is the case?
Yeah.
Okay, so let's see what it means. So what it means is that when we plug this into the functional equation, what will we get? We'll get okay, we'll get okay, maybe let's use the notation. It means we'll have okay, so the functional equation is P of T of X equals T of P of X, but now we're saying P is R of T, so it tells us that R of T of X equals T of R of T of X. Okay. But what it means then is that R of T of X minus T of R of X, okay, like has infinitely many roots. Does it make sense? Actually, not even infinitely. Maybe it's not even infinitely many. So I don't even have to write it like that. Maybe I can just be a little bit more explicit. So I can say, like I can say let T of X equal Y. And I'm saying R of T of Y equals T of R of Y. Okay. No, so Abdullah, you're asking a question. What are we trying to show R is? I'm not claiming I know what R is. What I'm claiming is that if P satisfies the functional equation, then so does R. And then we can induct because what's the point? R has a lower degree. So we go basically so what's the point? The point is yeah, so let's be a little bit careful. What exactly did we show? We showed that what did we show? We showed that R of T of X equals T of R of T of X. Yes. Okay. Sorry. I need to be a little bit careful, right? So yes, let's be a little bit careful here. Yeah, so I'm being a little bit messy. So let me just. Okay, so let's just let's state the claim. So claim 1, if P is even, then P of x equals R of x squared plus 1 for some R, for some polynomial R. And then claim 2 is that R of x also satisfies the functional equation. Okay, so are these two claims okay? Do people understand?
I think now maybe we can say that R is either even or odd. If R
Yes.
is odd, then R of x is x.
Right, so if R is odd, then R of x equals x, and otherwise R is even. Okay. So now what
And
does this mean?
we have a new S such that S of x also satisfy the function equation, and S of x squared plus 1 equal to R of x. And maybe we repeat this process.
That's right. So if R is even, we just repeat, right? So if R of x is even, then okay, we know it's even, and we just repeat. So that means R of x is equal to S of x squared plus 1, and we just repeat. Okay, so the point is, at some point we have to get a, yes?
So B of x must be like t applied case times of x for some k. From this, we can conclude. Yes, I think we can conclude that from this.
Yeah, right. So the point is, this process, either it has to stop at some point. And why does it have to stop? Because the degree is getting smaller each time, right? Like we know the degree of R is half of the degree of P. The degree of S is half of the degree of R. Okay, and so at some point we must stop because the degree is getting smaller. And when we stop, we know it's an odd polynomial. And we know it's P of x equals x. Okay, and so then yeah. Okay, I made a mistake. Does anybody know what a mistake is? I know I made a mistake because in the list of solutions, okay, I have P of x equals x. I have iterations of T of x, but I'm also there's one solution I'm missing. It's this the constant solution, right?
C?
Yeah, P of x equals C, or I mean there will be two of them, right? C, like there's two roots, but I'm missing those solutions. So where did they go in my where did they go here, right? So the point is
maybe because, when we have b of x equal to q of x squared, b will be b will be b will be equal to q. The
yeah,
polynomial
that's
will
the
be
point,
equal
right?
to q.
That's right. So this P and R, they become the same, right? So the point is, okay, there's actually two, like even with an even, there's two cases. There's the case where you have a constant polynomial and the case where you have a non-constant polynomial. If it's not constant, then the degree of R is actually smaller. Okay, because otherwise, if it's constant, P and R are the same. Okay, so yeah, so let me make a comment about writing the solution to this problem. So first of all, okay, this is exactly the kind of problem where people miss a lot of points for like not doing the thing. So let's I want to actually talk about how do you write the solution to this problem. So first, what is the answer? So the answer is okay, there's either P of X equals C, where C equals, I forgot what is the, C is a solution to which polynomial? C squared minus C plus 1. So in particular, C is a primitive sixth root of unity. Okay, or it means P of X equals T power kx for some k greater than or equal to 1, or P of X equals X. These are the solutions. So let's talk about how you would write the solution. So if I were writing the solution, I would do it like this. I would first say, okay, claim 1. If P is constant, then P of X equals C for, okay, so you can do this, fine. Claim 2, if P is odd, then P of X equals X. Okay, so this is the argument that you gave, Kram. And now for the last case, right? So claim 3, if degree of P is greater than or equal to 1 and P is even, then P equals T to the K for some K. And the proof is by induction on degree of P, okay? Because then when you come to this step and you have R, you can just use the inductive hypothesis. So you can say R is iterate of T. Does it make sense what I'm saying?
Yes.
Okay, so
We use induction of the degree of B.
yeah, so what does it mean? It means P equal, so P of X equals R of X squared plus 1. And then we show that R is, then we show what? We show R of X equals X, or R is even and satisfies the functional equation. Okay, so in the first case, we're done. In the second case, we invoke the inductive hypothesis. Does it make sense? Okay, yeah, so I think that's probably the cleanest way to write the whole solution. But yeah, any questions or comments? Okay. Let's see what to do now. So this problems are pretty tough. I didn't really budget enough time for the rest, so I guess we won't have time for everything, but that's okay. Yeah, so now I want to talk about today's topic, which is integer polynomials. So yes, polynomials with integer coefficients. So the first thing I want to talk about is these two problems here. Okay, so these are both about polynomials with integer coefficients. So what is problem 1 saying? So problem 1, or problem 2 here, it says that so both of them are okay. P of X is an integer polynomial. So the properties are, let's say A, B, N are integers. Okay. So the first property is that A minus B divides P of A minus P of B. Okay. For all integers A and B. And the second one is that is if A and B are congruent to mod n, then P of A is congruent to P of B mod n. Okay. Okay. So before I go and prove these two statements about integer polynomials, do you guys see how they're actually basically equivalent? They're more or less the same statement. Yeah, okay, so yes, they're more or less the same statement. So let's prove one from the other. So let's first prove that we can call them property 1 and property 2. So let's show property 1 implies property 2. Well, yeah, so how do you show property 1 implies property 2? So let's assume property 1. Now what? So we're trying to prove, we're assuming this, or we're taking this for granted, and then we're trying to prove this. So here, yeah, so what's the point? If A is congruent to B mod n, then n divides A minus B. But we also know that P of A minus A minus B divides P of A minus P of B, so it follows that n divides P of A minus P of B, and so P of A and P of B are congruent mod n. Okay, so that's the proof that that's the proof that property 2 follows from property 1. Okay, make sense? Okay.
Yes.
So then the other direction, that property 2 implies property 1. So let's assume this now, and let's deduce this. So what's the point? The point is that A is congruent to B mod A minus B. It's a funny thing to write because we usually don't write we usually write like we don't really write something weird in here, but it's true. A is congruent to B mod A minus B. And so it follows, if we assume property 2, that P of A is congruent to P of B mod A minus B, okay, which says that A minus B divides the difference. Okay. Makes sense? They're okay, so they're equivalent. Great, so let's show one of them. Really, you can, I mean, yeah, it's not hard to show either, but let's show the first one, okay? So how do you show the first one? Yeah, so you want to show that A minus B divides P of A minus P of B. Okay, it's a hands-on calculation. Let's write P of X equals Cn x to the n plus Cn minus 1 x to the n minus 1 plus C0. Okay, so what is P of A minus P of B? P of A minus P of B, we can group the terms like this, right? We can group it as Cn times A to the n minus B to the n plus Cn minus 1, A to the n minus 1 minus B to the n minus 1. Okay, all the way to the last term will be A minus B. And there'll be the C0 terms will cancel, right? Okay, so now we're basically done, right? Like each of these terms is divisible by A minus B because of our because of the great identity, right? So this is equal to A minus B times A to the n minus 1 plus A to the n minus 2B plus all the way to B to the n minus 1. Okay, and likewise for the rest of them. Okay, so it makes sense? Okay, good. So
I think we can do it the fact that say A to the n minus B to the n is divisible by A minus B. We can do it a different way. we say that A is congruent to B mod A minus B.
Mm-hmm.
So A to the n is congruent to B to the n mod A minus B.
Mm-hmm.
And
Yeah,
we,
great.
yes,
Yes. Yes, that's also a great way to do it. Mod A minus B. Yeah. But you know what I'll point out what you're doing here, Karam, is you're actually what you really do, at least what I think, you're directly proving the second statement. Really is what you're doing, right? And then you're saying, okay, they're equivalent. Okay. Yeah, so let's go and see how we can use this. So yeah, so where am I? I'm here. Yeah, let's use this one. So yeah, so I'm discussing what are some ways to use this trick. Okay, it's a trick. So how do we use this? So the problem is, suppose you have a non-constant polynomial with integer coefficients. Show that there are infinitely many primes, p, such that p divides p of n for some integer n. In fact, you can even say positive integer. I don't think it really matters. So yeah, so the point is, if we look at the sequence p of 0, p of 1, p of 2, and so on, there are infinitely many prime divisors of the sequence. Okay. So any ideas how we can solve this?
I didn't
actually,
get this question. What are we supposed to show?
Yeah, so
Are we supposed to show that there are?
Yeah, go ahead.
Yeah, are we supposed to show there is one n which p is divisible of all, or just
No, I'm
that there
saying
are infinite primes that divide the polynomial overall, like for different
it
n's?
isn't. No, I'm saying there are infinitely many primes that don't divide the polynomial overall, that divide just one term in the sequence. So let's do an example. So example, show that
uh,
there are infinitely many primes p such that p divides n squared plus 1 for some integer n. Okay, so I'm saying, or I'm claiming, there are infinitely many prime numbers that divide a number of the form n squared plus 1 for some n. Does it make sense now, Adam?
Yeah.
Okay. Okay, great. So yeah, so any ideas what we can do here?
I think we can prove it by contradiction.
Okay, so let's assume that there are only finitely many such prime p. Okay. Okay. Now what?
Now we assume that B1, B2 up to B sub k are all these primes.
Mm-hmm.
Then we consider B1, we plug n equal B1, the product of all these.
So you're saying take P of P1, P2, PK. Okay.
Which equal to B1, B2, BK up to BK squared plus 1. And this must have a prime divisor other than its distinct. This will not be one of these. So that's a contradiction.
Okay, great. So this is for specific. Okay, so maybe I should make a clarification. Is this, I guess, yeah. So this section here, we are talking specifically about the polynomial P of x equals x squared, right? So yeah, so this is maybe I can make it. Yeah, okay. So this is addressing this specific case here, right? And yeah, and so indeed in this case, this argument works, right? Because it means what? Yeah, it means we've constructed a new number that's not divisible by any of these finitely many primes. So it must have some other prime factor, and there's a contradiction. Okay.
It's like inspired from Euclid's proof of that there are infinitely many primes.
Yeah, right. So this is so in fact this is a version of Euclid's proof. So like Euclid's proof or Euclid's Euclid's proof is for the polynomial p of x equals x. Right.
Yes.
So this is a generalization for arbitrary polynomial. So how does it work? So yeah, so what are some ideas to do it in general?
I think it will be very similar, but
Okay, so
we consider, I think, the two cases or many cases. If the constant term was is zero,
okay,
then obviously it will have infinitely many prime divisors because we can consider b of 2, b of 3, b of all of
yes, so
all of
p
them
of is equals 0, then we're done. Yes, okay.
are not.
Right,
Case
we're done
2,
because x divides p of x, and so you can just it's equivalent. It follows from Euclid's proof. Okay, right. So case 2 is that p of 0 is not equal to 0.
we have two cases.
Okay.
We have suppose that there are finitely many primes that
Mhm.
satisfy the statement we b1 b2 up to bk.
So it's supposed for contradiction. Only finitely many such primes p1 through pk. Now what?
Now if we plug like we have b of b1 b2 up to bk, it will be equal to we can it will be b1 b2 up to bk times some integer m.
So let's okay, maybe should we write something like p of x equals x times the q of x plus some integer n, like this?
b of x equal I think
We can do this, right? We can just, I mean, n is just a constant term, right? It's whatever, c0 maybe. Just write it c0. Okay. Okay, so then this is equal to m times m plus c0, right?
and now we plug x equals c0 or I mean the product b1 up to bk. So we vector b1 up to bk from c sub 0.
You factor from c sub 0. I don't understand.
Uh,
Are you saying
I
are you
mean
saying I should take the common divisor?
no, I mean I'm considering now the case that b1 up to bk is divides c sub 0.
Okay, so let's say let's take a subcase now. Case 2.1, let's say. P1 pk divides C0. Okay. So now you're saying I look at so you're saying, okay, I think this expression, I can write it as I can pull out this and I can write it as m plus C0 over like this. and this is some integer.
Yes.
Okay, so now what?
Maybe if maybe M have like infinitely many values, and maybe for some values of M we have we can I mean that we can then plug like n times b1 up to b sub k for arbitrary many for arbitrary integer n, and maybe we can get some values of m that makes m plus c sub 0 over b1 up to bk is not divisible by one of these.
Okay, so we want to get something about M, but the thing about M is, what is M? M is another polynomial. M is like what, Q of P1 through Pk. So I don't know if the problem got easier or harder. I don't know. I don't know if it got, maybe, let me think. I don't know.
Can't we take P of C0 plus 1?
P of C0 plus 1. Okay.
We can
so
all,
what happens
in that case, there is a new, or actually, no, we can take, for example, the P of all the prime factorization of C0.
Okay, so if you take P of C0 plus 1,
you can factor it from everything except from C0, which means that there's a new prime that is not divisible by C0.
yeah, so if I have P of C0 plus 1, what it means is well, no, I don't know, right? So this is what you're saying, right? P of C0 plus 1, because, okay, what it's telling me is I have something, I don't know what to deduce from this. The only thing I can really deduce is that this is not divisible by C0 plus 1. I don't know what else to say. Like, it could still be divisible by C0, right? Because this is just what? This is equal to C0 times Q of C0 plus 1 plus Q of C0. But now I don't know. I mean, I have Q of C0. That's kind of like that could be divisible by C0, maybe not. I don't know. It could have a lot of things. Yeah, so this is kind of, I don't know how to get a handle on this, right? Because you want to, plug in something for X that forces you to have a new prime factor. Okay, let's do something. Let's do this. Okay, let's do it. Let's Okay, let's say we have some number, we have p of n, right? Now I want to, yeah, let's say p of n is some p1 e to the 1 all the way pk e to the k. Right? And now, can I plug in something, p of some m or something, such that it's forced to have new factors, new prime factors? Okay, so I have some p of n, and I want to produce a number that I somehow forced to have new prime factors. And then I can just repeat somehow. I don't know. Okay, maybe can I force it to have some of the same prime? Can I write down a number m so that p of m has all of these prime factors? It's guaranteed to have all of these. So I know n has these prime factors p1 through pk with some multiplicity. Can I write down another number that must have some of the same prime factors?
We want to have what?
So I'm doing something counterintuitive. Instead of forcing p of m to have different prime factors, I want to force it to have some of the same prime factors. Not all of the same, but just some of, like I just want it to have. Let's say I want to make it so p of m is divisible by all of these. Can I do that?
Okay. Okay. We have to m is congruent to n would be sub 1.
Mm-hmm. That's right. So you want to make it so n and m are the same modulo these guys. So for
Yes.
example, you can take p of n plus p1, or maybe in general, k like some, let's say t times p1. T is some integer, okay? Then all of these will actually be divisible by p1. Do you see why?
Yes.
Right? Because the input here, mod p1, it's the same as n, okay? And we know p1 divides n. Okay, so in general, if you want to, we can do something like, we can say, let's look at p of n plus t times. Now, instead of just taking p1, we can take p1, p2, pk, we can take all of them. In fact, we can even just take, yes?
Yeah, so we have that m is sum of these primes divides b of m if and only if m is congruent to n mod that prime.
No, not if and only if, right? Because
I think
definitely if, not only if, because it could be that there are other solutions mod p, right?
but if m is not congruent it's not congruent to n mod b.
Yes.
So we have m like is congruent to n plus l mod b, and l is not
Yes.
0.
Yes, but it's okay. So for example, consider the polynomial p of x equals 3x. Then mod 3, it's always divisible by p.
What is the tx?
No, I'm saying, so consider the polynomial p of x equals 3x, right? then it's true, for example, P of n is divisible by 3. But always, right? It doesn't
Yeah,
have
but
to do
yes.
I'm just explaining that it's not if and only if. It's just if.
Maybe the if and only if statement will be true when the constant term is not 0. I'm not sure.
No, it's true. No, it's kind of complicated. So let's consider the polynomial P of x equals x times x plus 1. This is always even.
Yes, but the constant term here is 0.
Sorry. Yeah, you're right. What I meant is x plus 1 times x plus 2. You see?
Yes.
But I could have given better examples. I could have given something like P of x equals 3x plus 3. I don't know. But there's a lot of there are other examples too that are like yeah. There's actually it's not okay. What you're talking about, and I think maybe we can there's a lot to say about here, but you're talking about solving polynomial equations modulo P. And the thing is, there can be multiple solutions modulo P. Does it make sense?
Multiple solution.
So, okay, like if I wanted to say, okay, when does P of n is 0 mod P, okay? And I have some solution and not. But there can be more solutions.
Maybe
Does it make sense?
Yes.
Yeah, so I think it's actually there's a lot to say about this, but it's actually very complicated. So I don't want to go down that route. Okay, so maybe you can yeah, there's a lot to say about polynomial equations modulo P, but I don't actually want to go that route. So because it's very deep, and so we could talk a lot. So maybe if you have something, you can ask. We can discuss it later. Yeah, but okay. What I want to I want to um I want to go back to this problem. So I want to say, okay, is there a comment?
Isn't the problem just showing the P of n is reducible for an infinite amount of primes?
P of n is irreducible. What do you mean reducible?
Like we can write it as the product of two polynomials with integer coefficients.
No, but P could be irreducible.
Yeah, we could just
Are you talking about irreducibility over the integers or modulo something?
oh, never mind. It has to be non-constant. I thought we could just write it as, like, for example, P multiplied by the same polynomial, but reducing it.
Okay. Yeah, I mean, so for example, if the example we did before, P of x equals x squared plus 1, right? The polynomial is irreducible. Sorry, I guess it was x squared, right? We could have said P of x. No, the polynomial is x squared plus 1, right? And yeah, so that was the polynomial here. And this polynomial is irreducible, right? So okay. Yeah, okay. Okay, let's okay, I think I want to let me just say the point I was making. So right, so we were talking about we have P of n, and these are its prime factors. Now I want to write down a number that is forced to have the same prime factors, right? So I could take P of n plus t times P of 1. Okay, this will force it to be divisible by P1. So you can also take t times P1 PK, and now it's forced to be divisible by all of P1 through PK. But I think there's something a little bit cleaner, which is just you write take P of n plus t times P of n. Okay. or you don't even have to write t, but you can write t of n plus something times p of n. This is forced to be divisible by p of n. Yeah, because does it make sense? Like modulo p of n, this number is equal to this number. Yeah. So like n plus t p of n congruent to n mod p of n. So p of that is congruent to p of n, is congruent to 0. Okay, great. Okay, but this is like the opposite of what we want to do. We wanted to produce a number that has new prime factors. Any idea how we can do this? So if we plug in, okay, we can, so yeah, so your comment is what? Your comment is that if we plug in something like p of n plus 1 like this, am I understanding your comment correctly? Oh, I see. No, you're suggesting something else. So you're suggesting this. P of n plus p of n. Ooh, like this. Okay. Okay, so let me understand. Let's see. So p of n plus t times p of n plus 1. Okay, so what we can say from here, let's understand. So modulo p of n no, so okay, so if I did this, what I would get is that this is congruent to p of n mod p of n plus 1. Okay. Which is, I guess, congruent to minus 1. But yeah, I don't know. It doesn't give me new prime factors, right? I don't get new prime factor, do I? Minus. Yeah, I don't think I get new prime factors from here. Yeah, so the trick here is what? So the trick is this. So the trick is this. So the trick is I consider p of n plus something times p of n. Now what do I put? I put here like p1, p2, pk. Well, let's just put p1 for now. So for simplicity, let's just put p1. Okay. So p of n plus p1 times p of n. So and we can put t or something if we want. Okay. So why is this good? Because it tells us that now we consider it modulo p1 to the e1 plus 1. Okay. Now mod p1 to the e1 plus 1, this one is divisible by p1 to the e1 plus 1, right? So this is equal to p of n. And okay, so it means, and what is P of n? So P of n is this. So in particular, it's not 0, right? Because it's divisible by P1 to the E1, but not P1 to the E1 plus 1. So the number we produce like this, it has a lot of powers of P1. There's E1 of them, but not E1 plus 1 of them. So, for example, in general, if I take P of n plus T times P1, P2, Pk times P of n, this number, it would always be divisible by Pi to the EI, but not divisible by Pi to the EI plus 1. Does it make sense?
Yes.
So it's very slick, right? By very precisely controlling the input, we made it so yes, it's divisible by P, but we controlled exactly how much. So now the point is it has to have a new prime factor, right? We need okay, either or. It could also be the same, but okay, whatever. Just take T very large. Take T very large, then you get a very big number, and it'll have a new prime factor.
Yeah, because for some T it will not be equal to B1 to the A1 times BK to the EK.
That's right,
So
yeah.
it
So
will have
or
a
the
new,
negative of that, yeah. That's right, yeah. That's right. So we need to rule out that case, but just take very big or something. Okay, and that's the idea. I mean, you can just keep doing this. So you can start with like, n, and then you can get n prime, n prime prime, and you just build a sequence like this. And you see you are always adding new prime factors. And so that solves the problem. Does it make sense?
yes.
Yeah. Okay. So, yeah, so what do we do now? So any questions? Okay, yeah, so let's go to the next problem. So I guess we won't be able to do everything today. But I do want to show this problem. Let me think. Yeah, so maybe okay, we'll do the next two problems. I guess we have another 10 minutes. Is it okay if we go like 10, 15 minutes over? So we have another 20 minutes, say 25 minutes.
Yeah, that's fine.
Okay.
Yes, it's okay.
So yeah, so let's do this problem. So you have a polynomial with integer coefficients, and you have this equality. It's like a cyclic equality, right? P of A equals B, P of B equals C, and P of C equals A. And you want to show that it implies that the three integers are, yes, it's important they are integers. So you want to show that they are all the same. Okay, so you have integer polynomial with integer coefficients, and you have integers A, B, C with this cyclic identity. And you want to show that A, B, and C are the same. So any ideas?
We need to first get a statement that's x is divisible by y, and at the same time y is divisible by x. Because
Yeah,
that
that's right.
implies that we can do this using that a minus b divides p of a minus p of b, and we get three cases. A minus b divides b minus c, a minus c divides b minus a, b minus c divides c minus a. Then we use the fact that they all divide each other and get three simultaneous equations involving absolute values. And after that, I just broke all of them by squaring all of them. And I got that A is equal to B is equal to C after long algebra.
Great. Okay. Yeah. So right. So we use this, this trick A minus B divides P of A minus P of B, and it gives us this nice chain of divisibilities, which
But
tells us that yes, come on.
but here we are assuming that A is not equal to B and B is not equal to C, because if A equals B, A minus B will be 0.
Yeah, so if A equals B, then okay, so let's look. What does it mean for 0 to divide something? I think okay, so maybe there's a matter of conventions here. So
Maybe we
let's see.
can.
Does 0 divide 1? Yeah, so does 0 divide? The answer is no. 0 does not divide 1, right? Because 1 is not a multiple of 0. Yeah. So, like for example, 1 divides 0, but 0 does not divide 1. So in particular, if A equals B, then B equals C as well. Does it make sense? So if A equals B, then B equals C. I mean, you can just see it directly, right? So like, what is it? If A equals B, okay, then I just look at the first two equations, and it immediately tells me B equals C. So if any of the 2 out of the 3 are equal, then all 3 are equal, and we're done. So we can just assume that they're all unequal to each other. Yeah. Does that address the concern, Karam?
Yes.
I got a question overall. In such cases, where we have to specify that we assume that, for example, A is not equal to B is not equal to C at the beginning. Overall in math competitions, IMO and other competitions, do we lose points if we don't specify that our math is rigid from the beginning? Like, can we just start with this, or do we have to specify that A is not equal to B from the beginning?
Well, if your argument is assuming A is not equal to B, you should write that I assume A does not equal B. But then you need to give an argument for when A equals B, right? Like you can in this case, I would do cases. I would say, okay, case 1, A equals B, and then B equals C, and so A equals B equals C. Case 2, A does not equal B, like this. Does it answer your question, Anham, or did I misunderstand?
No, I got it.
Okay, yeah. So now then we have this, and yeah. So there's a lot of ways to proceed. So one thing you said, Adam, you can do is you can square all of them, and that just removes the absolute values, and then you can do some algebra. I think also you can just you can say we can probably just say, but you can say assume A less than B less than C. And then it's clearly false, right? Like A and B can be equally spaced, but then and B and C can be equally spaced, but then A and C is bigger, right? So it's kind of can't be true. Yeah, I think that's okay. But I want to make a point, which is you can assume this at this stage. You can't assume it from the beginning because the given information is not symmetric, it's cyclic. So you actually cannot assume an order. But what you can do is you can say, okay, you can say lemma if A, B, C are distinct and A minus B equals B minus C equals C minus A, then A equals B equals C, right? Whatever, okay. Or, okay, yeah. And then for the proof, you can assume, like for the proof of, like what I'm saying, the statement of this lemma is symmetric with respect to A, B, and C, but the problem is not. Does it make sense what I'm saying? It's a subtle thing, but you can lose points. Like, okay. Yeah, so I'm saying like, okay, from the very beginning, I cannot assume that A is less than B is less than C. Right? Because the statement is not symmetric with respect to A, B, and C. Does that make sense? Okay, but the lemma is symmetric with respect to A, B, and C. So in the proof of the lemma, you can assume an order. It's just a subtle thing about when you, okay, it's called without loss of generality. We start proofs with without loss of generality. You need to make sure what you're saying actually is symmetric, but okay. Okay. Let's yeah, okay, good. So that solves the problem, right? So yeah. So there are a couple of problems on the homework that use this this trick. A minus B divides P of A minus P of B. Yeah, so hopefully there's some fun problems. So I want to go over some other ideas that are important for integer polynomials. So the first one is actually something from the previous not the homework even, the previous warm-up problems from the previous lecture, right? So we had this polynomial long division, which basically says, anytime you have A and you want to divide by B, you can do it, and there's a quotient and a remainder. Okay. And we stated it for, I think, complex coefficients or real coefficients. It also works for rational coefficients. So I can do polynomial division with rational coefficients, but I cannot do it for integer coefficients. So let me maybe state an example. Like if I want to say, let's say I want to divide like 3x squared plus 1 divided by 2x. Okay, already there's a problem because I want to put a rational number. Okay, and so like your quotient and remainder no longer have um, uh, integer coefficients. Does it make sense? So you can do it with rational polynomials, but not with integer polynomials. So that's an important thing. So does that make sense?
Yes.
But I want to point out that, okay, it doesn't work for integer polynomials, but it works if the one you're dividing by is monic. Okay, so it works. Let's write it. It works if, in this case, what is it? B of x, right? B of x is monic. And you can sort of see why. I mean, you can just, okay, in this case, I put 3x here. Okay, and you can see it'll work. So I don't want to prove it now. It's one of the homework problems. Or I uploaded. I didn't. I have to update the homework, but okay. I just before we started class, I added it as a homework problem. But yeah. So does it make sense? It works for monic integer if you're dividing by a monic polynomial. Then your quotient and remainder will still be integer. So let's see why this is useful. So let's say we have a polynomial p with integer coefficients, and we have three integers a, b, and c distinct. Three distinct integers a, b, and c, so that p of a, p of b, and p of c are all plus or minus 1. And you have to show that P has no integer roots. So let's give a couple minutes to think about it. Okay, so any actually do you want some more time to think, or should we discuss? No, do you guys want to discuss, or should we you want a couple of minutes? Yeah, yes, okay. I assume you mean yes to discuss, right? Okay. So let's um yeah, so what's the idea? So okay. Yeah, so does anyone have any ideas? There's kind of there's a trick to this one, which I think is okay. I don't know. Somehow this whole plus or minus one business is kind of not the red herring. We could have actually just got rid of it. So how do we do that? So suppose we have this polynomial P with this property. Consider Q of x, which is P of x squared. Okay. Then Q of x has integer coefficients, and Q of A equals Q of B equals Q of C equals 1. Okay. So this problem is just easier, right? We didn't have to say plus or minus 1. We could have just said 1. Okay. So what do we do from here? What is RRT? Rational return. So okay, I see. No, but actually, I think your first thought is because look, we have this is some common thing, right? Like you consider say g of x, which is q of x minus one, and this is great, right? Because it has roots, right? It has three roots. So you consider g of x, and so the point is okay, x minus a. That's how can you write? We can say g of x is equal to x minus a times x minus b times x minus c times some polynomial, let's say f of x, right? But here's the important thing. What kind of coefficients does f of x have? Okay. You can say it has rational coefficients, but does it have integer coefficients? And the point is that it does, because what is f of x? F of x is it's the polynomial division of g of x divided by x minus a, x minus b, x minus c. And so the important thing, this guy's monic. Okay, so because this polynomial is monic, and we know polynomial division works with integer polynomials when the one you're dividing by is monic, we know that f of x has integer coefficients. It's an integer polynomial. Okay. So in particular, it means we can write q of x as 1 plus some polynomial f of x times x minus a times x minus b times x minus c, where f of x has integer coefficients. Okay. And now, how do we finish the problem? We want to show that it has no roots, right? So, right, so the roots of q and the roots of p are the same because one is the square of the other. They have the same roots. So yeah, it's enough to show q doesn't have any roots. And so, yeah, why is that? Why does q not have any roots? Oh, sorry, it has no integer roots. No, it has no integer roots.
Maybe because the expression f of x times x minus a times x minus b times x minus c will not be equal minus 1 because a and b and c are distinct. So the absolute value must be either 0 or the absolute value will be bigger than 1.
Right, so if n is a root, it means f of n times n minus a times n minus b times n minus c equals -1. And you're right, so yeah, so this can't be plus or minus 1. That's just not possible. Because a, b, c are distinct, right? So it's not possible, right? So yeah, let's
And f of n is an integer.
yeah, right. So that's the point. So it's not possible, right? So okay, if their spacing is 1 each, then yeah, so okay. If the spacing is like this, then okay, then n minus a, n minus b, n minus c is too big. And if the spacing is like this, the problem is then you would have n equals b, right? And yeah, so there's something to check here. I don't want to go over the nitty-gritty details, but you guys see like this expression, this can never be plus or minus 1. Okay. Does it make sense? Do you guys want to go over the details of that, or is
Yes, because the absolute value of n minus a times n minus b times n minus c could not be 1.
well, it can be 1, but it can be 1 because then all of them would have to be 1, right? And that's just not possible.
Yes.
Yeah.
Because they're
right,
distinct.
because they're distinct, right? So you can have 1 is 1, where it's minus 1, and the third one would have to conflict, right? So okay. Great. Right. Okay, maybe I can just let's. I think it's worth doing. So what is the point? So the point is, okay, let's just let's do this. Let's make some space. So yeah, if this was true, then it would mean that absolute value of n minus a equals absolute value of n minus b equals absolute value of n minus c, which equals 1. But then what happens? Then n minus a, n minus b, n minus c are plus or minus 1, but then two of them are the same, and we have a contradiction. Because we have a contradiction because they were distinct. Okay, great. So yeah, I think maybe I should do this. So I'll go over another problem because it's very important, I think. So yeah, so this is called Gauss's lemma. And this is, I think, the most one of the most powerful tools for dealing with integer polynomials. So okay, and there are like three ways to state it. So we'll just focus on the first statement, right? So so a polynomial p with integer coefficients is called primitive. So it's a new definition. If the coefficients don't have any common divisors. So for example, if I take 3x squared minus 2x plus 6, this is primitive because there's nothing that divides all of the coefficients. But if I took 3x squared minus 3x plus 6, this is not primitive because all the coefficients are divisible by 3. So does the definition make sense?
Yes.
So in particular, what does it mean? So here's a maybe I'll call it a lemma. It's not. It's easier than Gauss's lemma, so I'll call it maybe a pre-lemma. Do you have a comment?
Maybe we can use visit identity.
Okay, so you want to prove it, right? But before we prove it, let me just state something about this primitive business, right? So it's a pre-lemma maybe. So if p of x is a polynomial with rational coefficients, rational, not integer, then there exists unique, let's say, R and let's say capital, what's called Q, R and Q of x, such that, so R is a rational number. It's a positive rational number. So not a polynomial, it's a number. Positive rational number. And Q of x is a primitive integer polynomial. And P of x equals R times Q of x. Okay. So the point is, if I have a polynomial with rational coefficients, there's going to be some kind of like a prefactor that's just a number, positive rational number, and a primitive integer polynomial. So, for example, here it would be 3 times x squared minus x plus 2. So 3 is your rational number, and then this is your primitive exponent of polynomial. Does it make sense? Yeah, okay. So like, okay, maybe like, for example, if I had like 1/3 x squared plus 2, this is 1/3 times x squared plus 6. Okay, so the 1/3 is the r, and the x squared plus 6 is the primitive polynomial. Okay, so right, so what we want to show now is that the product of two primitive polynomials is primitive. Okay. So Karam, you had a suggestion about Bezout's. What's Bezout's identity?
For the first exist x for this polynomial we will have sub x such that b of x equal 1.
Is that true?
No, I'm wrong. I'm sorry. I think that what I said is wrong.
Can we
I
do it
think
by
we
contradiction?
Yeah, we can do it, but let me just think a little bit about what Karam just said. Let me yeah, because p of x minus 1 doesn't have to have any integer roots, right? Yeah, I could have like weird roots or something. Yeah, so it's not quite true. Okay, 3 of x plus 5. Okay, now if I look at 3x plus 4, it has no. Yeah. I think yeah, you can create examples where like it doesn't have rational roots even. So yeah, I think it can be kind of complicated. Okay, yeah. So okay, Adam, you're saying we should proceed by contradiction, right? So yeah, so that's the right idea.
Yeah, we assume p of x can be written as, let's say, f of x multiplied by g of x. Then
Right.
we just take two random terms for each of f of x and g of x, assuming that they're not divisible by a certain prime. Then we can
Right,
go
so
to
hold
show
on.
that.
Well, let me just let me write down what you're saying. So okay, so that we're all on the same page. Okay. Yeah, so you're saying, so what do we do? We assume that p of x equals f of x times g of x, where f and g are primitive,
Yes.
but p is not. Okay, and then so we're saying there exists a prime, little p, such that okay, little p divides all coefficients of big P, right? So is that where we are?
Yeah.
Okay, and then what do I do?
Then we can just take two terms of f of x and g of x. For example, ai a sub I x to the power of I and bj x sub b sub j x j, respectively of f of g, for both for f and for g.
Uh-huh.
And
Okay.
we show that p cannot divide all of the terms of f and all of the terms of g.
Yeah, so you want to show that well, we want to derive a contradiction, right? So we want to show okay, let's go like this. Let's We want to derive a contradiction. So, okay, we know, let's go like this. Let's say we know f and g are primitive. So we know, so we know p divides all the coefficients of the product. Okay, so it divides all the coefficients of this guy.
B must
Yes.
divide f of x, one of f of x or g of x for infinitely many x.
You're saying, okay, so you're saying, so you're saying p divides f of, okay, you're saying,
No, we're saying that p of x is not primitive, so p divides p of x. But f of x and g of x are primitive.
No, but so Kram's comment is this, right? So Kram's comment is that since p divides all the coefficients, it means that for all integers, let's say k, p divides f of k times g of k, which means for all integers k, p divides f of k or p divides g of k. And then by the same argument, this like this like I have an infinite set I can split into two, right? So it means either there are infinitely many integers k such that p divides f of k, or infinitely many integers k such that p divides g of k. But now, you see, this is actually not a very strong statement, right? Do you see? Because actually, okay, what does it mean for p to divide f of k? As long as p divides f of k for some integer, it's going to do it for infinitely many integers. By this, it's what we showed before, right? That's like once p divides f of k naught, then p divides f of k naught plus tp for all p. So it's what you said is true, but it's not actually a very strong, it doesn't give us that much information, I think. Because we're trying to deduce something. What? We're trying to deduce from p divides all the coefficients here, we're trying to deduce that either p divides all the a's or p divides all the b's. So yeah, so that's what we assume p divides all the coefficients of the product. Do you want to prove that either p divides all of the a's or p divides all of the b's? Now,
don't you want to show that if f and g are both primitive, then p does not define p of x? That's
okay,
our contradiction, because by definition, we have that p divides, small p divides the polynomial p. But we create a contradiction, because if we get a term, since p divides capital P, and by definition, then we have that p does not define f of x, and p does not define g of x, since they're both primitive. So we take a random term of f and a random term of g, such that both terms are not divisible by p, and we see the product in the polynomial product, and we see that p does not divide that term, even though by definition it should divide it.
No, the problem here is, okay, so you can find it. Okay, so okay, you're right. I can find okay, I can find something where p does not divide AI, okay, and p does not divide bj. But now it's not true, because if I look at AX the I, Like if I look at, you're saying look at the x to the I plus j term. The problem is the x to the I plus j term, it has ai, bj, but it also has other stuff. Like, you see, so it's not actually, like we can't conclude that the coefficient here is not divisible by, sorry, what I meant ci plus j, okay, like ci plus j, the coefficient of p, it's gonna have more than just ai and bj, right? It's going to have other terms. Does it make sense, Adam?
Yeah, the
So, okay, I think it's easier to do this when like in like a there's too many like this like there's way too many coefficients. I think I need something that's uh like let's do a case, right? Let's do like two quadratic polynomials. I think that's better. Okay, so let's consider f of x equals a2x squared plus b plus a1x plus a0 and g of x equals b2x squared plus b1x plus b0. Okay. And okay, so we know p divides all coefficients of the product, but p does not divide all a's, and p does not divide all b's. And then we want to derive a contradiction. Okay, right, so we assume p divides all the coefficients here, but since f and g are primitive, it doesn't divide all the a's and doesn't divide all the b's, and we want to derive a contradiction. So yeah, where can we start? I think one place we can start is, okay, let's just say if p divides a0, b0, that's the constant term. So it means p divides a0 or p divides b0. Okay. Okay. Now what? Now we can look at the x term. So for the coefficient of x, it's going to be a1, b0 plus a1. Okay, so yeah, we can get p divides. So, right. Let's do it like this. Let's say without loss of generality, p divides a0. And then what? So yeah, so then the point is we cancel this term, and so p divides a1. Okay, and I think you keep going. So then what? So then you have p divides a2 b0 plus a1 b1 plus a0 b2. And yeah, so then these both are divisible by p, so it tells you p divides a2. So it's like this. Like you just so it's okay. You assume, so p divides one of the two constant terms. Let's just assume it's the constant term of f, and then you just sort of induct by coefficient, and you'll see that p divides all the coefficients of f, and there's the contradiction. Does the argument make sense? I didn't try it. Did I go too fast? Should I explain it again? Okay, are you guys still there?
Yeah, I'm just writing out what you said.
Okay. Okay, should I explain it again or I don't know. Okay, let's do this. I think maybe it's just okay. It's kind of late, and we've been doing this a long time. So maybe we can pause here. Maybe I'll just say this. To prove this, just understand the case when the two polynomials are quadratic, and the argument will go like this. You first look at the constant term, and without loss of generality, you'll see. Okay, the point is p divides one of the two constant terms, and without loss of generality, it should be the constant term of f. And then you kind of just induct. You go term by term, constant term, linear term, quadratic term, etc., and you'll see the contradiction. Yeah. So okay. Yeah, so I think maybe we should just take a break and we can maybe continue this next time. Are there any questions before? Are there any questions before we break?
What will be the topic of next week? Also, is it going to be also polynomials?
No, I think it's. I don't know, unless you guys really want to do polynomials, but I think maybe I don't know, three in a row in polynomials. I don't know, probably it'll be geometry or something. I have to think. But yeah, I will finish the proof of this next time. But also you kind of need this for the homework, so I don't know. But yeah, okay, I'll finish the proof of this next time, and then we'll switch to a different topic.
Okay.
Yeah. All right.
Thank you.
Yeah. Okay. All right. Thanks, guys. Yeah, and so we'll meet again. Where is the recording? Did it stop? Ah.